Okay, so hi everyone. So we're happy to have today. We're happy to have Idan Schwartz. So Idan is a postdoctoral scholar in the deep learning lab in Tel Aviv University. He's collaborating with Leo Wolf, and he earned his PhD in computer science at the Technion, working with Alexander Schwing and with Tamir Chazan. Idan's research is centered around cognition in deep learning models. This includes attention models, multimodal problems, and multimodal bias removal, specifically tasks such as visual question answering, image captioning, and visual dialogue. We're happy to have you. Yeah.
So I'm happy to be here. Sorry for the short notice. Just announced it yesterday. Thanks everyone that could join. I'll pass this slide because Safir described it already perfectly. And I'll start with the main motivation of this talk, at least for my eyes. So as he said, my thesis is more about trying to solve cognitive tasks, for instance, visual question answering. And during the process of thinking about those problems, we're trying to kind of separate the task into different ideas. And one of the things that a model will need to have the ability to do is to comprehend an image and understand the objects that exist in the image. And this is the main motivation for zero-shot tasks, the way I see it, because in order to process and understand any object, we will need to have a lot of data. And when we talk about supervised supervision, usually we don't have that. So in this talk, I will show how to utilize big data sets, something like LEAP, and I'll get into details next, in order to solve, let's say, image captioning in a way that will comprehend all the objects in the image. So when we think about comprehension in supervised methods, usually the idea is to take something like VIT or ResNet and have a big pre-training on a task that have enough data like classification, and then fine-tune it to a different task. So if we look on those big data sets, so for specifically classification, ImageNet has about 1.28 million samples, and it's a number I think it's important to remember when we come next to CLIP. So this is the way we comprehended all the objects in the world like 5 years ago. We had a pre-trained model on ImageNet, so we only based our comprehension on 1.28 million samples. Which sounds a lot in 2015, but we'll see it's not. Now, more advanced techniques for multimodal tasks usually use pre-trained models on larger scale, something like 6.5 million. And then we still have the fine-tuning part. And the fine-tuning is basically taking all the 6.5 million image text pairs that we pre-train and gain knowledge on, and kind of like compress it to a very specific task based on a much smaller scale of data. So let's say we are going for captioning. If we can have pre-training on 6.5 million pairs, but then again we'll have a fine-tuning that only takes the 100K samples that we have in Coco, for instance, and base all the comprehension or solving the task on them. So even if in the 6.5 million we manage to have good comprehension on objects, when we fine-tune, it corrupts this knowledge, and we will show that. I will show that next. So what is the next phase in comprehension? So we talked about 6.5 million and 1.2 million. So CLIP has 400 million pairs. So this is a whole new scale of data. And I think this is why it's so exciting to work with CLIP, because suddenly we realized that many of the things maybe we're trying to have in a representation, something like compositionality, we maybe achieve it just by training on large scale data. And the idea in CLIP is that it only gives you a matching score because it's trained based on contrastive learning. And it means that if you give him an image and give him a text, it will give you a score how much they correspond to each other. But it becomes difficult when we will try to take this knowledge and transfer it to a new task, something like image caption. So how we do that? So another model that is important to generate and not just to have a matching score that we use is the big language models that we have available now. So GPT-2 trained is a language model that's trained on 8 million web pages, and it will be the tool that we will use to generate the language. So what we want to do is to have the comprehension of CLIP. CLIP knows, in a way, any object that exists because it looks on 400 million pairs. And now we want to create, let's say, caption that describe an image based on GPT. This idea is not fine-tuned at all. That means that we haven't restricted anything, like we haven't only looked on 100K samples to create captions. And what we get from it is something that is completely new. So if we want to have a little bit more motivation, so why we need this amount of data. So this is a tweet from Jan LeCun that says that a 5-year-old boy observed in self-supervised learning during his life, something like 788 million frames that includes not only visual, but also touch and audio. So even intuitively, we know we need this amount of data to get to a place that we can imitate human behavior or human way to describe images or the human-like ability. This is just something small to motivate things a bit further. And just as a side note, I don't want you to get out of the start like I'm thinking that we only need to rely on more data to improve models. This is just a small example, and I admit it's also promoting a new work we just published. But if we have better supervision, we can improve the model, let's say, to perceive the correct object in the image. So in this new paper that we published, optimizing relevancy maps to improve robustness, we actually gave something like segmentation of the objects as a supervision to change the places that the model looks on. So it is something that is also important to improve perceptiveness, to know exactly where to look. So this is something else from understanding what the object we look at. So I think data is very important for comprehension, understanding what exists in the image. But other things like perceptiveness, look on the foreground and not on the background, those are other things we need to improve. And this is one way we taught the model to look on the objects and not on other things. So what are the things we are now achieving with more data? So for instance, this is something that is very visual and easy to grasp. So text-to-image models are now much, much better. And we know that the model have improved, but it came along with data, and we have to remember that the data also contributed to those things. And what I will talk about in this talk is actually the other side of the coin, how we also get the same improvements when we look at image to text. So in image to text, this is actually the most basic task that we solved. Even classification could be attributed to image to text. We have an image, we want to get a textual class. It might be overlooked, but this is a very important direction to get a text from an image that explains the image. So one idea to do that, and this was published along with CLIP, is to do classification just based on prompt engineering. So as I mentioned in CLIP, you have an image and a text, and you get a score, a matching score between them. So if you make a text for a photo of something, and then put all the classes of ImageNet, you could get a score for each class, and you'd get in high percentage the correct class when the prompt is given with the class that we refer to. So if we want to, for instance, to classify pets, we could change the prompt to a photo of a label, a type of a pet. So this is really engineered and ad hoc solution, but it does work. So it gives us some intuition how to maybe start doing those things, but it's not enough because we do need a closed set of classes in order to use this approach. So we need to have 1,000 classes, and each time ask this question with a different prompt. So on the right, we see zero-shot improvements. There was a big increase using CLIP as a solution from all the approaches previously. So we do get the feeling that we can solve other tasks like classification based on CLIP that wasn't specifically trained for classification. So this was the first, what started the initiative of all the zero-shot, new zero-shot approaches that came along with CLIP. So I will show next our approach. I wonder if there is, like, usually there are questions during the talk, or no? It's up to me. So this is just motivation up until now. I will show our approach, but if someone has questions and want to bring up something, let me know. So our approach wanted to have the same zero-shot capabilities, not rely on any supervised data, but now for captioning. And here you can see 3 examples of images. Our approach gave something that is completely different from all the supervised approaches. And keep in mind that those approaches are based on pre-training of millions of samples, but they are all fine-tuned for captioning based on COCO, for instance. So on the left, real-world knowledge. So we have a hat here. Now, we have CLIP-VL and VinVL. CLIP also uses CLIP as a pre-training model, but again, we have the fine-tuning on COCO, and it gives us a blue hat sitting on top of a black table. VinVL gives us the caption or a police hat sitting on top of a toilet. Now, both of those results are plausible, and I'm sure if you ever use captioning models, you'd say, okay, it's correct. But when you are going completely zero-shot and not corrupting the representation at all with any fine-tuning, you could actually get that this is a cap from the Toronto Blue Jays 2010 season. I'm not sure if this is actually the correct season, but it is the Toronto Blue Jays. And also, when you look on the captioning on the middle, they are much more diverse and human-like. So both of the supervised approaches, when they create a caption, it almost look the same thing. And keep in mind that the pre-training is completely different, and those are two different architectures. And yet they both produce something that almost looks exactly the same. And I feel like this is what we usually get from any model that we interact with any machine learning model, that it's kind of like a dull outputs and repetitive. And this is something, if we want to change it to be more human-like, you can see that zero-shot approaches give something that is more resembling what human would say about this image. And on the right, we also show that OCR, for instance, is something that the model does, even though we haven't really gave him any supervision that is specifically for OCR. So again, with a lot of data that the model is trained on, he learns how to ground words as well, which is interesting. Another thing I want to talk a bit more is a metric that we look at, which is the vocabulary that our model uses. So with our approach, the number of novel words are above 8,000. And this is significantly higher than all the supervised methods. And this, again, just to motivate you that, yes, there are some things that zero-shot methods will never achieve, like it will be very hard to come close to supervised metrics that are based on human references, because all the supervised methods are trying to imitate the supervised humans that usually been trained to answer in a specific way. But we do get something new. We have now much larger vocabulary. And with that, like, we might be able to refine it to a place that it will also be perfect, but it is a new direction to create captions. Okay, so I started with the results and now move into the approach itself. Now, it's not that complicated, but it does require some background in how transformer works, so I'll quickly go over it. But just like the high level, you have a language model that generates a new word. Now, let's say the sentence that the language models restarted from is image of it. We gave this initial words, and we asked the model, give me a new word. Now, here we have the context of the language model. This is what I'll explain next. But intuitively, what we would want is that the model, let's say, instead of generating image of a bald man, because there is an eagle, will shift the output of the language model to eagle instead of man. How we will do that? So we have two losses that we use during the optimization, during the inference, like we optimize the model during the inference. And those two losses are corresponding to two different tasks. The cross entropy loss, which is the fluent language fluency loss, will try to keep the word fluent, like to keep the entire sentence fluent. So it means that it will try to get the new logics, the output of the optimized output. It will still keep it close to the original output. So it will not be too far away from what originally the language model gave us. The other loss that is based on clip will take the output and ask clip, what are the tokens that work better with the image? Now, this is a process we do for every word. So obviously it's a much slower technique. There are new methods that are trying to improve this disadvantage. But again, in this work, at least, we haven't focused on this aspect of making a caption in a millisecond, but we focused more on creating human-like captions and in a zero-shot approach. And here, if we run an iteration for a few times that shift the context based on those two losses, it will shift from man to even. So this is the main intuition to how we create a captioning model in a zero-shot manner.
I have a question. So is the language model here, is it first fine-tuned on image captions, or is it just a pre-trained model on normal text?
So excellent question. So the language, in our approach, we haven't fine-tuned it at all.
Okay.
This is why we get real-world knowledge, and I'll show that. There are other approaches, more recent ones, that started with fine-tuning on captioning. So it will make the entire process much faster because the optimization wouldn't need to be that dramatic, or even with no optimization at all, you could get, let's say you just ask Clip immediately, which token gives you the highest score you would ask Clip on each question which token give you the highest score, and you just pick those without any optimization and it will work. This is a paper called Magic that does that. But the language that it generates, it's completely, again, you fall back to the same problems, like it becomes dull and
interesting.
Yeah.
And do you think there's like a way to get the best of both worlds by like
I think
less
so.
Fine-tuning, or I don't know exactly what.
This is exactly the challenge, and I think this is where the research will need to understand how to do that.
Yeah.
But definitely, but we need to avoid fine-tuning. This is the main message. It corrupts all the comprehension that we got. It corrupts.
Interesting.
But you sort of do fine-tuning also here, right? I mean, you're just using these unsupervised losses.
So we are not basing the optimization on any supervised data. This is the idea. It's just on Clip. Now, for us, Clip represent the real world because it's trained on 400 million pairs, and like maybe.
So this optimization process. So which parameters are being optimized? Is the language model's parameters? So
the language model is frozen, but it takes a context, and the context is optimized. Like it takes input a context, and I'll explain how the context is created. It's not that interesting, but the idea is that the key and value representation, if you know a little bit about transformers, so they are frozen during the inference because you never look on the future, you only look on the past, and this is why you can optimize them. You can treat the representation as parameters that you optimize. So you change the context. I mean, intuitively you change the context that gets into the language model, but the language model itself is still frozen.
So this optimization is ad hoc. It happens to
every token.
For every new token,
yeah,
and for every single, like one image, one token.
Yeah, this is why it takes time.
And how much?
Like 5 iterations is enough, but you need to do it for every token, so it's slow. Like not very slow, but it will take you about 1 minute to generate a sentence. In this approach, like you could easily think of a way to optimize that, like cache and stuff like that, but we left it for future research.
Can I just clarify, like real quick? So for the language model, so thinking something like GPT-2, right, or something like that, is it basically prompted with image off, and then you let it say what's more likely thing to say, and then you every time you guide it with Clip? Is that basically the?
Yeah, every new token you start from scratch and optimize the context that gets into the language model.
But like, do you prompt it with an image off or something like that?
Yeah, we started with image off, but this is again, it's like an hyperparameter. Like you could start with different things. Let's say you want OCR, you could start with image of a sign that says, or something like that. So.
Right. But so language model in this case is purely language. It's not multimodal. It's like GPT or similar. Okay, thanks.
And you could make it multimodal, but I feel like it will restrict the output again to something that might not describe everything, because the language model is trained on 8 million web pages, which is quite a lot. And I don't think there are many multimodal data sets that are that big. So I'll quickly go over it because we already discussed it, but just the idea of what exactly we optimize. So in transformer for each token, we get the value key and query representations, and we multiply the key and the query, we get a score for each token, and it tells us which tokens are important. And then we aggregate to each token is neighbors based on those scores. So this is transformers. Works great. The idea in decoding is that we mask the attention. It means that when we create the key and query for a token, it only looks on the past because we mask all the futures. So it means if we are now creating key and query for the second token, during the decoding of the fourth token, it will not change the representation of the second token. So it means that the second token is only based on the past. This is why those representations are constant for each new token, and we can optimize them. So now you could think on all the past representation as parameters because they are constant. It's not like every iteration step, like every time you optimize the token, they will change. This will probably be hard to make it converge. They are constant and we can keep optimize them. So the decoding looks something like that. You could just think on the key and value as set of parameters that define all the past. And with the loss, we basically just use gradient descent here to update those key value presentation.
So you optimize directly the key and values
Yeah,
as
the
if they
output.
were weights?
Yeah, not the weights that created the representation, the output. This is great. So you got it. This is exactly.
So for example, the MLP that is usually used to generate the key and value.
Mm-hmm. We don't touch it because the language model is frozen. Every parameter.
It's not just not touching it, it's not used because the key and value are now.
Yeah, we only keep the key and value. And this is the decoding idea and use them as constant. It's some optimization that came with GPT-2. So it's quite common, and you can optimize the context instead of the actual key value weights. Perfect.
Sorry, one technical. So when you move to the next token.
Yeah.
So how do you initialize the key and values?
So it starts from scratch. It's not where we stopped last time. So optimization starts from scratch.
From scratch meaning random, or from scratch the result of the original MLP?
Of the original.
Also another question. Can you explain again what the cross entropy loss is between?
Right. So I think I have it here. Maybe. Let's see. Yeah, maybe not. So the cross entropy loss is just taking cross entropy between the original output of the language model and generate like we do it 5 times.
Oh, I see.
So every time we want, like, there is an hyperparameter that calibrates between those losses, but without it, it will go to something very random. Like you could find a sentence that Clip says it's perfect, and it doesn't mean anything. So you want to keep the language flow. So here again, it's just an equation that says that the clip loss we calculate for every token that the language model outputs. And for efficiency reasons, we only look on something like the top 20 tokens, and the rest we just say that their likelihood are 0. And so there are many ways to think of how to optimize things here, but this is already plausible. It's reasonable. It will be hard maybe to run on a million samples data set, but if you just need one caption, it's not that bad. And so we get potential for each token, and then again we use cross entropy loss. And the inference, as I already said, it is a gradient descent approach that take the loss and do 5 iterations to update the context of the language model. Okay, so few more examples. And I think what's important to take from here is the idea that the supervised methods, the language, it's very repetitive. So we can see that clipvl and binvl, a toilet sitting on a ledge or a white toilet sitting on a sidewalk, but both of them kind of fail to understand it's a rooftop and it's an installation of something new, like our method approach did. In the boat example, you could see that our method kind of tried to ground the text, the Tolkien text. So you could see a boat with message on the side saying token. Maybe it's not perfect, but try to do that. Or you could see here a meal that it does look like a flight meal. Maybe it's not true, but it does look like a flight meal being served. And the other just say a tray of food on a table. Both of them said, both of the supervised approach said almost exactly the same thing, because the fine tuning, you miss a lot of things. And on the right, again, another example of more diverse and human-like results. So this is cool, but it's not the coolest thing. I'll get to the coolest thing in one slide. So real-world knowledge, as I said, it's very good. Like it could realize it's a trump. Now this is something like this goes to your question. If you fine-tune the language model only on captions, you'll never get something like Trump or Simpsons. Those like you can't comprehend those ideas because they are completely gone when you are doing fine-tuning. OCR, as I mentioned, works as well, which is kind of surprising. And the next idea that we explored is arithmetic with visual. So this is something that no one, I think, ever thought could be, we could get to that before with any other method. We couldn't think of a way to get that. Now, what is visual semantic arithmetic? So what would happen if, when we have the clip loss, that we are computing potential for each new token based on it. So we take encoding of the text, encoding of the image. This is the e-text, e-image. We use clip and get a potential. What would happen if we take two images and compare the encoding of the text to, let's say, sum of both of them, of these two representations? So what we see is that when we are trying to generate a caption based on an encoding of two images, we get something interesting. We get something like taking the concept of another image. So for instance, a phone plus an apple, we get Apple iPhone as caption. If we take Canada and a tree, it will give us Toronto Maple. And we did the same thing with the subtraction. And I think this tells us a lot about clip representation in general, because what we got can show us the way the compositionality of clip. Like we have compositional thinking here, because if we take a caricature illustration of a plane and subtract the plane, we'll get a caption of caricature illustration. We just showed you that what we are left with is just the concept of caricature. If we take many balls and subtract one ball, we get a caption of a bunch. Shows you a little bit about this way to maybe capture many versus one. We have an image here of a zebra inside a cage, and we subtract a zebra, we'll get jailed or imprisoned. And on the right, we have the concept of night, and maybe something about different times. So this is something very interesting because I think there is also some of the debate how we can get compositional thinking. And Clip does that. Maybe it doesn't do it all the times, but with a lot of data, it does have compositional thinking in his representations. So we took it a step further and we tried to merge those two ideas of subtracting and summing up representations. And we got to arithmetic. So we have the famous examples from NLP, from word to vec, where we have a king minus man plus woman equals to queen. So we can do the same thing with images, which is something new. And for instance, if we take a chicken minus an egg, it gives us like a direction of food. So if we add it to a cow, we get a cow's milk. And it also allows us to ask questions visually. So if we have Obama and we make the direction from the US to Obama, so it's like a presidential vector. Now, if we add it to different flags, we'll actually get, maybe it's not the current one, but we will get the leader of the country. So Angela Merkel, Cameroon, and Putin.
Why do you need the brackets?
So just to help you understand what's going on, because the subtraction gives you a direction. So it's kind of like you need to think about it that you have the concept of president, which can be added to something else, and it will shift the output based on it. Yeah, so it's something that's to help you. Some other examples. So we have here the CEO direction. So CEO of like Bill Gates and Microsoft is the CEO of Microsoft. When we add it to Mark Zuckerberg, we get Facebook, Apple, and Tesla for a different example. And some other ideas, for instance, Italy and pizza. It's something like pizza is food that relates to Italy. So when you add it to a baguette, you'll get France. We have something about the capital of a country, of which country, or you could ask yourself things about, let's say, I think it's Russia, and again, the capital of Russia, which is Moscow. When you add it to France, you'll get Paris.
Sorry, could you say again which particular embeddings are you using in this case? This wasn't just clip, right? You are showing something different. Could you remind?
Yeah. So again, when we optimize, when we have the clip loss, originally we just took the encoding of the image and the encoding of the text, and we created potential for each token based on that. Now with arithmetic, again, we use clip encoding. So we encode the image, the two images, and we add them together. So it kind of shows you the abilities hidden in clip representation. Does that answer your question?
I guess mostly, yeah. I would probably need to check out the paper a bit closer. Like we played with clip directly, and we we couldn't quite get it to behave that nicely. So what do you think that makes this arithmetic work in your case?
Yeah, so it doesn't work all the time. This I agree, but it does work significantly amount of times that you know that something like it's not random. And we even have a data set that we try to measure that. So I'll go directly to the data set. So we created this data set. So as you can see, it's not always working. So in the paper, you'll find this data set that shows like those visual questions, like from building to a country, country to capital, CEO to company. We show that it works in some of the times, but compared to ClipCap, for instance, that it is a supervised approach, it works significantly better. So I think, yeah, it's better to look into that, but it's just a beginning of something that we couldn't even think of before. So yeah, and if you have more questions, I'll be glad to talk about it. Just another small thing is that obviously because you have clip is what we use to encode things, we can also encode text. So we could create those direction based solely on text. We could have image of a night minus image of a day, and it will create the direction from day to night. So then when you add it to breakfast, it will actually say dinner. And the same example with Tokyo and Japan, like you could have one of the encodings based on text and not image. Okay, so this is something you better look in the paper. It's a data set that we created to measure how good we are. And I want in the time that we have left to talk about a more recent work that we try to extend this approach to videos. So this is the caption we created in the new approach. And the challenge with videos is that you don't look only on one image. And we can just sum up all the frames and tell the captioning to generate the GPT to generate text, because it's not going to be stable enough and consider all the different things that are happening throughout the video. So we needed to think of a way to improve the way we generate text. And why I'm saying it's not stable enough. So think about it, that what we are doing here is every time we generate a word, we do the optimization from scratch. So it's like a person that's starting to say something, and every new word you can shift the entire thing he was starting to describe to a different place. And now if you do it for one image, maybe it's okay. But if you do it for 5 images and you tell him each time, give me the word that describes those 5 images the best way, it will be very tough. And I think even for humans, you understand that it's hard to find one word that describes 5 images. And these are the main disadvantages in any attempt to take the original approach that I just described to video, because multiple images are difficult to describe with one word. The optimization, is not likely to work. But it will be easier if we could describe all the images with a whole sentence, with the entire sentence. And we know that multiple images require some coherent narrative, and we want to keep this coherency. So it will be easier if we could let the model to describe a complete sentence and optimize it coherently the entire sentence altogether. So this is what we try to achieve. Instead of optimizing each token each time, optimize the entire sentence. So the way we did that is, instead of just optimizing the context, we optimize pseudo tokens. So pseudo tokens are randomly initialized tokens that basically don't describe any word, but we keep their representation during the entire optimization process of the complete sentence. Now, the way we did it is we started generating words for a sentence, and we accumulated all the losses. And during the generation of the sentence, we changed the pseudo tokens. Every time we got to a new sentence, we just started again to generate another sentence, but the pseudo tokens remained the same. So now the optimization tokens will get better and better in describing sentences. But we are not starting from scratch for each word, and we keep the pseudo tokens during all the sentence we generate. So the pseudo tokens evolve in each sentence we generate. So let's say we started by generating a sentence we just optimizing based on the, as I said, each token we generate, we do just one step of optimization. We are not optimizing until we get to a convergence. So it starts generating the sentence, And we got something like a very bright flash of light that appears to be coming from the sky, something that is not very specific. So it's still kind of close to what's happening in the image, but it's not coming any close to what's really going on in the video. So every new sentence, the pseudo tokens are still remain as like we keep optimizing them. So on the fourth sentence, the caption starts to talk about anime, like we have a Naruto flying away in a flash as he appears with the full moon and sun, something that is more close to the world of actual Goku from Dragon Ball Z. When we get to the 20th sentence, it actually describes Goku flying through space with a giant beam. So with those pseudo tokens, we are able to optimize the entire sentence, and it's much more coherent than we had in the previous approach. So any questions on that? Hope it's intuitive enough, this idea. So let's see some results.
Sorry.
Yes.
Are you also optimizing the prefix tokens? Just as
No, so the prefix tokens are constant.
Okay.
Thank you. And we don't even optimize the context. We just optimize the pseudo. This is that.
I'm curious, have you been able to look at the pseudo tokens and like, I guess the tokens are like already embedded, but have you tried to be able to invert that embedding and see what maybe the tokens represent too?
We haven't tried, and that's interesting to kind of maybe see what a good prompt could be. But I'm not sure it will be easy. Okay, so video captioning with the zero-shot approach, how it looks like. So again, we have the two first methods are fine-tuned. Those are two different architectures. They both generate the same caption. And the thing is that with video captioning, the data that people fine-tune on is even much smaller. And obviously videos describe so much more things. So it is even a worse case. So you see with fine-tuning, you usually get the same thing. And it's so surprising because you can see architectures that keep improving, but in the end, they don't generate something that is dramatically different or better. Now, zero cap is the previous method I just described, and magic is another method that I don't have time to get into. Both of them are zero shot, but they are dedicated for images and not videos. And you can see that they fail to describe anything close to actual real world knowledge of this is a video commercial of Samsung, this is an advertisement, and all the things that you can see in the last caption that our method was able to generate. So it's not really comparable, to be honest. One of the main benefits is that we are also see that with our approach, we can capture different frames and refer to them. So if we have a frame of audience, and some of the other frames are about a man that is talking, we get them both in our captions, the audience laughing and cheering about the joke about the comedians. And one thing I haven't talked about yet is how we pick the frame. So just quickly, we take clip representation of each image and we compute the distance between the different frames. And every time the distance is bigger than a threshold, we take it as a frame to look at. So this is also a very simple way to pick different things that are happening in one video. So this is how we pick the frames. Another question I haven't talked about is, okay, so we generate from a set of images, but we haven't even discussed about temporal information. So what we've noticed is that the language model itself kind of capture the temporal that it needs to have when it generates the text. So both the language model and also Clip already consist some temporal knowledge, because for instance here, when we took the sentence, the ball goes in the hoop after the man throws it, so it's much more likely. So this is why the perplexity is much lower, and also Clip score is better. So they capture that the man needs to first throws the ball, other than a sentence of the ball is thrown from the hoop to the man. Because you can see in small nuances that it looks like the man is actually throwing the ball and not the other way around. So this is about temporal information. And this approach, we also applied it to images. And it does give us much more coherent captions. And we see it specifically in the perplexity of the captions that we generate. The perplexity is measured with BERT. I'll just show you a few examples. So those are all zero-shot approaches, but let's say we have here an image of Bill Gates. So we have in zero cap a genius CEO is not a genius in the world of Silicon Valley billionaires, something that I'm not sure, because again, the token optimization could sometimes create sentences that correspond to the image, but not very coherent. Magic, which was fine-tuned on image captions, loses the entire ability to describe Bill Gates. So we have just a man smiling while holding a glass of wine. So this is, again, this is approach that fine-tuned on the language model, only the language model on captions. And you can see that it's no longer able to describe Bill Gates. Now with our approach, it's something completely different. Microsoft billionaire and philanthropist Bill Gates, who is the chairman of the foundation, and go on. This is really nice. This is something that really describes well the image, and we see it in many different images that we took from the internet about real world knowledge and not something from just plain Coco. It's something new. And that's it. I think we're on time. I'll be 5 minutes late. So code for both papers is already published, so feel free to explore it and let me know if you have any questions about it.
I need to run to a meeting, but thanks. It was really nice.
Perfect, thank you.
Do you have time for one more question, or are we very much late?
Yeah,
Sorry, what?
all the time in the world.
Just like, I mean, it's a bit philosophical question, I guess. Maybe it needs, a separate conversation, but like you've identified your goal quite clearly, toward more human-like captions, if you will, right? You want them to be, somewhat more interesting, somewhat more natural. It's not quite an objective which can be easily measured, right? It's not really something that could quantify easily. All the automatic scores just kind of go down. The diversity is high, but like, can we actually make any conclusions about how accurate these captions are? We can't really, right? Like, there's no easy way to measure correctness.
So such a good point. I feel like we should not only spend time on improving our model, but also improving our metrics, because the supervised metrics are not good, and showing improvement there doesn't mean anything. Like, we tried many different approaches to measure unsupervised with unsupervised method. Perplexity is one good way. Clip score, other methods that will come by that measure distance between image and text might be a good way. But to be honest, like we will need to have
have you tried human evaluations at all?
Yeah, exactly. So we've tried human evaluation on a small set. Like, we couldn't think of a best approach to do that, but definitely if someone can come by with a set of unsupervised metrics that will capture that, I think it will be very important for future progress, because it's missing at the moment.
Yeah, I mean, something that I was just thinking, that where might this method be, having some limitations or failure modes, is, you know, we've seen mostly success cases, right? You haven't really touched so much on the failures, but I could imagine that when we are talking especially about the zero-shot scenario, when it's powered by these large-scale language models, it might be prone to hallucinate stuff sometimes, which is just not really in the image, right? And with these metrics that you have right now, you wouldn't be able to capture that, to measure that. So that is one concern which seems to come up, in particular in video, because in video, like you said, oh, language models have some notion of what's like temporally, you know, coherent or meaningful to say. Glib has some knowledge, but I'm not sure I would agree that Glib has much temporal knowledge. But anyhow, the point is, it's if the video would be showing something unusual, the captioning model might just end up saying something conventional. So it might not be as sensitive as, you know, to some more unusual aspects of such a video.
Yeah, you are absolutely correct. And this is the main pitfall of zero-shot at the moment. It's something we will need to work on. And the hallucination is something we see a lot. You could see images like a Shutterstock or anything that comes from the data that Clip was trained on, you could reveal it with our approach, which is also something nice to understand from this approach what data Clip was trained on, but it's definitely not enough. Like we have in our paper more than Clip score. We took Blip, if you are familiar with, but we can't replace human evaluation.
Yeah.
I feel like perplexity is actually quite good. I know it doesn't describe the image, but at least when it comes to hallucinate random words, it will kind of capture that, because BERT is probably not likely to like if you have a word like Shutterstock in a sentence out of nowhere. So,
yeah, I can see how that can capture some of the issues, but
again, it's not multimodal. Yeah. I know.
Thanks so much. Yeah, thanks for your answers. That all makes sense.
Yes, I had a quick question on top, kind of like related to that too. Then I know a lot of people complain that, I guess, like, it's really this is really cool, by the way. So I think it's really interesting. I guess your hypothesis kind of that like all this knowledge is already in Clip, right? And maybe like part of the fall, like, you know, kind of the dilemma right now is that we don't really have like the right like methods to extract information out of these like Clip models. I guess, like, what is your take on, like, I know a lot of people say, you know, like you were saying, like compositionality is like something that people don't really see present in like language models, and, you know, more so like Clip. Like, for example, if I ask, like, you know, classically, like, oh, I want like a red block on top of like a green cylinder, things like that, right? Do you think the information exists in Clip and is like represented well, or like, and like the problem right now is that we just can't get to that through like natural language? And do you think like techniques like this could maybe tease that information out of the models?
So I think some of it exists, but you could easily find situation where it doesn't, especially when you are talking about temporal relations and all those issues, that it can easily find sentences that Clip wouldn't figure out correctly. So it's easy to find problems with Clip, but I feel like it probably works in places where there's so many examples, because in the end, even when you are just matching text with image, if the text does care about the relations, it will capture that.
Exactly.
So I feel like if you have enough data and you've seen, like, maybe we'll need to generate specifically images that talks about the trying to measure or capture things like relations. But currently it's easy to find places it doesn't work, but in our approach, we see that sometimes it does work, and it does give hope, like that maybe just data is the solution, or maybe we can get to something more human-like in the representation and mitigate all those pitfalls in a way that is more based on data and not on ad hoc models or trying to add our priors.
Yeah, like fine-tuning.
Yeah,
like that.
exactly.
Yeah, because that seems like a big takeaway too. It's like you said, like fine-tuning destroys a lot of.
Yeah, if you fine-tune just for relations, it will work, but obviously it will no longer will be able to describe Obama. Like, it will immediately corrupt that.
Yeah.
This is the problem. Okay. Right. If there are no other questions, thank you everyone who came and everyone in the Zoom chat. It's really nice being here. Impressive building. And I will go to a hike near Berkeley afterwards. So
It's a good choice.
yeah, it's a nice place. Thank you, everyone.
Great work.
Thank you.
This is super cool. Thank you very much.